So there is a first translation theorem that says, or the second translation theorem that says, if we want to find, if we know the transform of L of f of t, or the Laplace transform of f of t is f of s, and a is some number 0, then when we multiply our f of t minus a times our unit step function at t minus a, that comes out as e to the negative s times f of s, and the proof we've already even looked at. But there's a second form for the translation theorem, and the second form for the translation theorem is a little different. When we want to find the Laplace transform of g of t times our unit step function of t minus some number a, it's e to the negative as times the Laplace transform of g of t plus a. And this is true since if we do this, the step function is going to make 0 everything up until t equals a. So we'd be evaluating, it'd be 0 plus the integral from a to infinity, but 0 is still 0. So e to the negative st g of t, and that, if we make the substitution t equals u plus a, so u equals t minus a, then we're going from 0 to infinity of e to the negative s times u plus a times g of u plus a du. But e to the negative as is a constant and will factor out. So there it is, factored out, and then this with just e to the su here times g of u plus a, that's just the Laplace transform of g of t plus a. Actually g of u plus a, but it doesn't matter what variable we use, so we'll call it g of u plus a here, but it really is g of t plus a, and I think you can see that without too much hassle. So, easy one. Find the Laplace transform of sine of t times u of t minus pi. So, g of t is sine of t, a is pi, so g of t plus pi is sine of t plus pi. And that means negative sine of t, because this is sine of t cosine of pi plus cosine of t sine of pi being 0, so negative sine of t. So therefore, this transform is this part factored out, e to the negative pi s times the Laplace transform of sine of t, which is 1 over s squared plus 1. And then, of course, the negative of that, and then times what we'd factored out, e to the negative pi s.